Let's go. Odds. AJ. 97. Anything before that? Jackie. 5C. 5C. Okay, let's start there because this one's using our calculator, I think. Oh, no, it's using a table. Okay, so on 5C, you were supposed to already have made a table and plot the points. And then C says, eliminate the parameter. Okay, come on, kids. You were having fun with this, at least kind of, on Friday, about eliminating. What's eliminating mean? Take them out, right? How do we take out T? What do we do first? No. What do we do first to eliminate T? Isolate him. Got to get him alone, right? Got to get him alone off on his own. Then we can go ahead and target him and try to take him out. Come on. You were doing all right on this on Friday. So we've got to isolate him, and then we substitute. So where do we isolate him in? It's very particular where we isolate him in. Do we isolate him in the X or in the Y? Good. So we take this little X guy, take him off to the side, and we isolate him. This is for letter C. That's what Jackie was asking. We isolate by, how do we get rid of a square root? So we can say x squared is equal to t, right? Now what do we do once we isolate t? We erase his identity. We get rid of him. How do we erase his identity? Substitute. Substitute. So we can say y is equal to 3 minus who? Not t. X. Does that make sense, Jackie? Dun, 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 dun. Okay. Any other questions before 97? Okay, so then go into number 97. I went too far. There we go. Where are you, 97? There he is. Okay, this is the path of the football problem, which is very similar to our water balloon that we were doing on Thursday. Okay? So with the path of the football, a quarterback releases a pass at a height of 7 feet above the playing field. So can't I say 0, 7 is the initial point? Does that make sense? When t equals 0, for this pass, when t equals 0, I'm at the point 0, 7. Does that mean the quarterback is 7 feet tall? Nah, come on, think about it. What's the hand do? When it releases, it goes over the head, right? So he might be like, I don't know, 6 something, but either way. Releases, oh yeah. You have to be able to see over all the players, right? Anyway, so a height of 7 feet above the playing field, and a receiver catches the football, at a height of 4 feet. Oh, that's down here somewhere, right? The receiver catches it maybe down here, down here, down here. Or he's just really short. Well, I guess 4 feet. No, because you tuck it. Oh, that's weird. Anyway, so 0, 4. We'll say maybe he, whatever, we're done. So down here, 0, 4. Not 0, 4. Wait a minute. I don't know where that is. I know it's 4. Something 4. Does it say how far down the field? Oh, yeah. 30 yards. So I have my x, which is how many yards down the field. I have my y, which is the height off the ground. The pass is released at an angle of 35 degrees with the horizontal. Oh, is it measured in feet? Thank you, thank you. It wouldn't be 30 feet then. If it's 30 yards, how many feet would that be? Good. Good catch. Dimensional analysis, huh? Got to make a match. Write a set of parametric equations for the path of the football. Write a set of parametric equations for the path of a football. Do you guys get that this is going to be a parabola? Right? Now they do have this weird little like 35-degree thing going on, like at the angle at which it was released. So my parabola is a little funny looking. Sadly, my orientation is a little off. There we go. So that angle is 35 right there. And then I have a parabola as far as the motion of the ball. This one says see exercises 93 and 94. I think it gives you a little hint as to how to deal with an angle to get some equations. So I'm going to go ahead and peek back exactly where they told us to. We should use our resources, especially when they're cheating and giving us stuff like, oh my goodness, hey, all we got to do is follow the formula. All we got to do is follow the formula. So I have this up here. It says a projectile launched at a height of h feet above the ground at an angle theta. They told us exactly what to do in order to fill in. So if I use this formula, and if I just read the directions, I can follow, hopefully you can follow directions. So it says v sub naught, and when you look up here, the initial velocity, v sub naught, So I'm just going to put v because I don't think they told us that. They didn't tell us how fast. I'm not sure why that just moved, and I apologize for whatever it did just do. What are you doing? Huh. Something's possessing the computer today. All right, let's try again. Okay, let's see if we can do it now. Okay, what's the angle? 35. And then we have t. That's going on x. Then for y, I have h. Wait, h is the, if you just look right here, what height was it launched from? We already figured out it was 7 feet, so that'd be 7. Plus, and we have v sub naught, don't know him, so let's put v. And then sine of 35 times t minus 16t squared. And you might think we're totally stuck, except they did give us a hint. They told us that 30 yards or 90 feet down the field, the ball was at 4. So I could go ahead and say, wait a minute, I know a special x and I know a special y. I know when x is 90 feet, and I can put my v cosine of 35 t. I know that y is going to equal 4. The receiver catches it at a height of 4 feet. And that's going to be my 7 plus v sine minus 16t squared. Kiddos, how do I solve 2 equations with 2 unknowns? Yeah, system of equations. Now we could try elimination, but elimination looks like an awful idea. So if elimination is an awful idea, maybe we should think of substitution. Which one looks easier to solve and plug in for? This equation or that one? Yeah, top one's way shorter. Let's use him. Now, I see a t in 2 places. I'm not so sure I want to solve for t. I have to plug it in twice. Let's solve for v. He's only in 1 place. So I'm going to go ahead and solve for v. So v is equal to 90 over cosine of 35t. I can go ahead and take that v and plug into the other equation. And when I plug into the other equation, I end up with 4 equals 7 plus, and I could just plug in. No idea. It's okay. We'll just go with it. Yeah, I don't know. Can I get rid of it? I can. See? Not me. Where are we at? 90 over cosine 35t. That's v, sine of 35. T minus 16t squared. Oh, hey! What happens to the t's? They cancel. Hey, what can I do with sine over cosine? Tangent. So actually, I can make this a little bit nicer. And hey, can't I move the 4 over to be with the 7? Right? I can combine some like terms. So I can end up with subtracting the 4. 0 equals 3 plus 90 tangent of 35 minus 16t squared. Now we can do this in multiple ways. We can do this like algebraically. And to be honest, if I can get my calculator up, that wouldn't be too bad. You wouldn't have to use your grapher. You could graph this whole shabam right here, and you could find the zeros. So you could graph this side, and then you could find the zeros on your grapher, which wouldn't be impossible. It might just be a little bit messy. But the other way is that you could just solve this. And to solve it, let's see, what would we do? We would subtract the 3. We would subtract the 90 tangent of 35. Double check your mode. I think we were in radians a lot of Friday and Thursday, so you might want to go degrees. Just kidding, you have to go to degrees. Do you guys know you can skip to the end of your line of code by doing second over? Huh. Tangent of 35. Then when we have that, we'd have to divide by negative 16, trying to get to that t squared. Then we'd have to square root both sides to get to the t. And we'd end up with 2.031. Oops, that's not the one I want. I want this one. T equals 2.031 seconds. The set of parametric equations is what we basically kind of started with up above. Oh, hey, that's the wrong problem. What are they asking for in part A? Oh, we've made our equations. Find the speed of the football when it's released. That's going to be v. And then d. Oh, we already found time, so we actually answered d first. That's kind of awkward, but that's all right. Guys, once we solve for t, can I plug back in to find v, which is what they're asking for in letter b? Okay, so I have letter d right here. The equations that we made up above was letter a. For letter c, no, for letter b, we could go ahead and plug in, and so then we can say v is going to equal cosine of 35 times 2.30, nope, 031. In your calculator, be careful. Just a few of you guys don't use the nifty alpha y equals fraction trick for whatever reason. Those of you that use that trick, it'd be super easy to plug this in. You would just do your 90 on top, and then on bottom you would do your cosine of 35. Make sure to end that parenthesis, because then that's multiplied by your 2.031. But for those of you guys that type this in, be very, very, very careful. You have to do 90 divided by, and that's totally okay, but you have to put a parenthesis. You have to make sure you have that whole bottom line in a parenthesis. Otherwise, you're going to divide and then multiply, and that's not what we need to do. So make sure you put that parenthesis, cosine of 35, and then do your, don't end the parenthesis yet, times your 2.031. If you do division to show your fraction, you have to make sure the whole numerator and whole denominator are in parentheses if there's multiple pieces. There we go. So v is equal to the initial velocity that quarterback was throwing at a speed of 54-ish feet per second. So v would equal 54.0, was it 09 something? 096 feet per second. Thanks, guys, for keeping me honest with the 30 yards being 90 feet. If I hadn't paid attention to that, all these answers would be horribly wrong. And that'd be very sad, right? Were we missing? I think we're just missing 96 and 90, or sorry, not 96, letter C, which just says to use a graphing utility to graph the path. So we would go ahead and take those equations that we're supposed to be using, plug in the information that we just found, and we could go to our parametric. And we could graph our v sub naught. We got to be 54-ish. I'll just be super approximate. No, I can remember 54.096. Is that right?
Yes.
Okay, forget it. I'm going over here. 0.096. V sub naught cosine of 35 degrees times t. Don't plug in the specific t. We need to make it the equation where we have x of t. And then on this one, I could do my h, which is initial height of 7, plus my v sub naught, which is 54.096, sine of 35 degrees, t, minus 16t squared. You guys just told me that it was like 90 feet down the field, so I'm going to make sure that my window goes, I'm going to do 2 pi instead of, I could do zoom standard. Zoom standard, start there, but then be like, no, no, no. Did I put a minus? Minus 16t squared. Oh, I want it in radian mode. Sorry, not degree. I'm going to switch back. No, because I need degrees for cosine. Stink-a-dink. I would change your window to 0.1s, because otherwise it's not going to show you. It's just going to go by like 7 seconds, and then after 7 seconds, probably the whole thing is done. So we got to go by like 0.1s instead of by 5s or 10s. And then in our window, make sure that we go down to at least 90. I'm going to go to 100. That way we go past where it hits the ground. Let's see. It starts at 7 feet. I don't know. How high do you guys think the football will go? A guy who's releases at 7 feet, ends up at 4 feet. How high does a football go when you throw it? 20? We can do 50 just to be safe. Does that sound good? Okay, no. Well, I think you're about right, because look, if I did 50, this looks to be around 20, right? So let's go ahead. See, it says to find the maximum height, so I can go ahead and just use the cool max feature. Oh my goodness, stop graphing. You know what? We're having it go 360 seconds. That ball was only in the air like 2. So let's 10 instead of. There we go. Should stop graphing one of these days. There we go. So I can do second trace. I can find my maximum. Oh, how do I find my maximum? Oh, approximate. Okay, approximate. They knew that the parametric mode doesn't actually find maximum. So approximate, what do you guys think? It looks like 21-ish? 22-ish? Yeah, 21.9. Oh. Yeah, I'd say 22-ish. That looks good. 22-ish. It says approximate. Dun, 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 dun. Good odd questions. Good odd questions. Thank you, smart person who got the scissors and passed it around so people can trim it up to be what they want. That was a really good idea. Let's go ahead and check our evens on 10.6. All right, what evens do we have? Number 14. Is there just A and B on these? Yeah. All right, kiddos, there's number 14. Let me give you a second. I know we're doing a little bit weird. For some reason, my answer key didn't save from last year, I suppose. So number 14. Our next one is number 28. These ones you were graphing with a table showing the orientation. Make sure you put the arrows, because those are important. Make sure you put the arrows. It's supposed to show the direction of the movement. And then eliminating the parameter. Number 28 was one of those cool, like, hey, we want to use one of those nice trig properties in order to solve. There's number 28. Next one is number 44. I'll give you a couple more seconds on 28. .44 was a nice little, just put it in your graphing calculator, play with your window and try to figure out what's going on. A couple more seconds on the long one. 28 had some work to it. There's number 44. If you only got part of it, that just means you weren't necessarily all wrong, but maybe you just couldn't get your window. Maybe you just couldn't get your window to be quite what you wanted it to be. Our last one, I think, is number 58. Does that look right? Okay. 58 had a little more work to it. There was actually a special formula that could have been used. And we'll peek at that for just a second. But there's number 58, and that's our final even. In our notes from Friday, let me go back to section 10.6 for just a second. We didn't actually write down this formula specifically, but we did kind of do a few things that hopefully kind of helped. In that, we did do an example where I had an H and a K being added. It ended up being the H at the end and the K at the end. What was different in this example is I did secant tangent, and it ended up being a hyperbola. We also did an example with, that's not going to work, with an ellipse. I didn't put an HK on there, but I did show you how the 2 ended up being the horizontal minor radius. The 3 ended up being the vertical major radius. So put those two ideas together, and maybe you were able to figure out there's actually formulas for conic sections in polar or parametric. I'm not going to make you memorize these formulas, but they're there. So that's what this problem was trying to have you figure out. If you had gone back to exercise 31, you would have seen these little formulas and just plugged in. But you had to find the HK from conic section work. The HK is halfway in between. So halfway in between -1 and 7, well, that's a distance of 8. So go 4 from 7, that would be 3. 3, 3. The distance is your A, that's going to be 4. Your foci, you could have also gone halfway in between there and seen that it was 3, 3. Your C was equal to 2, so they just used conic section tricks in order to go ahead and plug in what they needed to know. So A was the horizontal measurement, that's why 4 went, oh no, 3, negative 1, 3, 7, sorry, vertical measurement. So that's why it went with the Y. Your K was the Y value, why it went with the Y. The H, the X value, and then the B went horizontally, and that's why it went with the X. Anyway, that was just getting a conic section, making you guys review a little bit of section 10 point, where were ellipses? 10.3? Yeah, 10.3. Making you review a little bit of 10.3 and play with parametric equations. With that, kiddos, we're at the end of our evens. I'm coming back to double check, but 58, good, good, good. Odd, odd, odd. All right, 10.7. Have those polar graphs made it all the way around? Okay, number 97, we ended up just doing that in or off to the side. And number 58, you guys didn't ask about, and we just graded it. Okay, here we go, 10.7. Our job today is to figure out how to graph these points. Kiddos, the way it's looking, we're going to go ahead and take today probably and a little bit of tomorrow to finish up 10.7. There's kind of a lot going on in 10.7, not that it's horrible or horrendous. And then we'll have our 10.6, 10.7 quiz on Wednesday. So we're going to do a lot more polar today. Remember, it's like section or chapter 9b with probability. It's like chapter 9b with probability. So it's just 2 sections, just 10.6, just 10.7. We're skipping 10.8 and 10.9 for a few different reasons. I think we're plenty warm that we can appreciate the cool air now, so let me get that going. Instead of starting off freezing and then having to adjust. You're freezing right now? No. Oh, exactly. Right before you walk outside, right? Okay. We'll try to make this a tradition for, May. Anyway, so, you're welcome. 10.7. I think we just have the last few who need to get this into their notes, but I think you already have your circles. You guys already have your circles? Okay, yes. Perfect. So Ryan, I'll come steal that from you. Thank you so much. Polar. You guys figured out on Friday that it seems, no, not quite, that it seems like, although, wait, polar bears live where? The Arctic, which are near the poles, and the poles look a bit like this. True? Yes. Latitudes and longitudes, we're not going into that right now, but latitudes and longitudes. Latitudes and longitudes. Right? Couldn't this be the North Pole, South Pole? Polar. Interesting. Anyway, so, exactly. But we're not going into that right now. Okay. So polar graphing, you can think of it polar ice caps, pole, North Pole, South Pole, etc., latitudes, longitudes, etc. But that's not exactly the point necessarily of what we're doing. We're just trying to get an introduction to how this whole type of graphing works. And as you guys saw in your calculators on Friday, this graphing is very different, very weird. And first of all, the window is kind of complicated to know what to do with, but once we do, we should see, or you should see, usually spiraling. Some sort of spiraling, some sort of curling, some sort of curving as you graph. So I don't remember what we put in our graphers on. Ooh, hold on. This window is way out of whack for what we're trying to graph. There we go. So there's spiraling, there's curving. Definitely, like, functions aren't a thing with vertical line tests. Like, that's not really a thing for parametric or polar. That's more rectangular. Wait, it was only half the graph. Remember, we had to change our window, so sometimes the domains and ranges are a little bit weird. So I would need to go, I'm in degrees right now, to 720, because the period was twice as long. It got stretched out. So the spiraling, how do we do this? Well, we saw at the very end of Friday that the order pairs look different. The order pairs are not x's and they're not y's. They're r's and they're thetas. If you guys look at your polar graph, don't you see angles? Don't you see thetas? So where do you see r's? Where do you see radii? Where do you see r's? And where do you see radii? Don't you see circles? Pause. For x's and y's, aren't there tick marks on the x, horizontal measurement, and on the y's, vertical measurement, right? Tick marks. On polar, you have tick marks going out diagonally along different radii. So a radius has a tick mark of, or a radius is 1. Then for the next circle, the radius is 1, 2. And then for the next circle, the radius is 1, 2, 3. You have tick marks that are going diagonally along these angle markings. So if the radius is 1, it's going to be somewhere on this one inner circle with a radius of 1. If the radius is 2, then we're somehow out here on the 2. If it was 1.75, it would be 1, and then, I don't know, right about there, 1.5-ish. So these are only showing some radii. They're not showing all of them, or else it'd be just a black dot, a black blob, because there'd be infinitely many, and you wouldn't see any white space. So these are just a few for tick marks. 1, 2, 3, 4, 5, 6, 7, 8. Now, how many circles are in yours? I don't remember if it's the exact one or not. It goes out to 8? Okay. So let's graph a few points. What if I was to want you to graph, and let's graph and label like we did in the olden days. Let's do A. What if I was to ask you to graph 3 and 75 degrees? 3 and 75 degrees. Where do you guys think that would be? In the old-fashioned, in the XY first quadrant, second quadrant, third quadrant, or fourth quadrant? Good. You look at the 75-degree line, right? It's called technically a radial line. 75-degree line. Start at the pole. Ooh, the pole, not the origin. The pole. And move out 1, 2, 3 tick marks. And that is point A. Does that make sense? Okay. What if I was to ask you to graph point B to be 8, 225. Okay. 8, 225. Third quadrant, you're right. The old-fashioned, there aren't really quadrants in polar, but yeah, the third old-fashioned third quadrant. You start at the pole. Imagine you're a person on the North Pole. And you're going to turn with a little compass from due east. You're going to turn 225 degrees. You haven't gone anywhere. Okay, third quadrant. This radius of 8 says go out 8. What direction? Towards 225. So turn 225, go out 8 towards that angle. Yes. That's what a positive radius does. It says head towards the angle. All right, cool. 1, 2, 3, 4, 5. Didn't you guys tell me it ends at 8? Isn't 8 the last one? Just okay. Now, what if I was to ask you something like point C, 0, and 285 degrees? Why would it be at the pole? You don't go anywhere. So you're still standing at the pole. Sure, you're facing 285 degrees, but you're at the pole. Wait, question. Hold on. That begs the question. Is there another way to stay at the pole? What's another point that would make you stay at the pole? 0, 0. Sure, what else? 0, 345. 0, 135. 0, and... Okay, whoa. How many ways can you stay at the pole? A lot of ways. So pause. What is the point of the pole? 0, 0, like the origin? No. There are infinitely many. Anytime the radius is 0, where are you? At the pole. Interesting. What if I was to tell you to graph? Ready? Yes. What if I was to tell you to graph -3, 150 degrees? Yes. Start at the pole, facing, for you, your guys' perspective, facing due east, okay? At the pole, due east. You turn 150 degrees. That's second quadrant, right? If I'm at 150, technically a little bit more over there. If I'm at 150 degrees, negative says head towards, no. Heads away, head away. Now, if I'm heading away from 150, what am I technically heading towards? Ooh, look at you guys. So couldn't I say that letter D is -3, 150, or +3, 330? Yes. Same point. Oh, so now we're getting introduced to the idea that one location can have many different ways of getting there. Now, they still have to follow certain rules, 1, 2, 3. Still have to follow certain rules. You can't just say like, oh, any point will get you there. No, that's not true. But there are many different ways. So I want you guys to think about if you're walking in the hallway, you know, sometimes you're like, oh, hey, and you like go towards someone. Or sometimes you're walking and you're like, you go the other way, right? Okay, so positive relationships, you're going to head towards. Negative relationships, you're going to... Okay. You do it. Me in the store when I see students. Just kidding, just kidding. I live in Santa Clarita. I rarely see anybody. And I always am like, oh, hey. And they're like, Okay, so... I see Ryan Murphy at Roscoe's. And we hang out, and it's good. Yeah, the missions team, sometimes we hang out. IHOP was the last time Angela and Ryan and I went and had breakfast before school. Okay, does it kind of make sense how you graph R's and thetas? Are R's and thetas X's and Y's? No, but are they ordered pairs? Yes. In what type of graphing? What's this whole thing called? Polar equations. So now that we've talked about points, I don't know why people are out early. Don't worry, we still have like 2 minutes. Oh, we already did that. Can I show you guys how to graph points without the polar paper? Okay. So what if I was to want you to graph, I don't know, what do you guys want, positive or negative? Negative. Okay, well, I heard more positives. Let's do 5, and let's do 135. That's a 45-degree angle in the second quadrant, right? Yeah. What if you didn't have the polar graph, which you're not going to have in homework, you're not going to have on the quiz, you're not going to, okay, wait, that's really complicated. No, it's not. Ready? Draw your X, Y, north, south, east, west. Put 5 tick marks in every direction. Why in every direction?
Because you never know which way you're going to go.
You're traveling on circles, so you have to have a circular. Now, question, for this 1 point, do I need all the circles? No. I only need the one with a radius of 5. So I can go ahead and mark 1, 2, 3, 4, 5 in this direction, 1, 2, 3, 4, 5 in that direction, 5 in this direction, 5 in this direction. All I'm thinking about is this circle, right? And then I need to think of what angle? 135. And where the two intersect, that's my point. So what if I was to ask you to graph the point? Let's do another one. We'll call this one, what are we on, like E or something? Let's do one more. What if I was to do 3, 60 degrees? Would it make sense to maybe do the 60 degrees first? Would I put, no. I only want it to be 3. Oh, I go over, no. I go up, no. I rotate. And when I do my imaginary rotation, because you don't want to make it super messy, couldn't you just say, oh, hey, look, it's right there. Do you see how you don't need a polar graph? You just need to know, turn an angle, and then think of the rotation and where the two intersect. All right, cool kids. That's it for today. We knew how to graph points in polar. We'll do equations tomorrow. Bye, guys. Maybe start homework as long as it's graphing points. Adios, au revoir.